The next AI bottleneck may not be inside the model, it may be outside the fence. A billion-dollar AI data center can have the chips, the customers, the cloud contract, and the funding, and still not be real AI capacity, because one plain gray power transformer can decide whether those servers run or sit waiting, not the transformer architecture inside an AI model. A power transformer, that is what gridlocked means. And this is no longer just an infrastructure detail. On June 18, 2026, FERC ordered the regional grid operators under its jurisdiction to justify or reform how they connect data centers and other large energy users. That is a huge signal. It means the AI buildout has become large enough to force a basic power system question. Who gets electricity first? Who pays for the upgrades? And how fast can massive AI loads connect without pushing the cost onto everyone else? That is why this episode is not about whether AI demand is real. It is about a harder question. Can AI spending become usable AI capacity on time? Because AI spending is not AI capacity. A signed cloud contract is not usable compute. A server rack behind a delayed power connection is not usable compute. A campus waiting for a substation upgrade is not usable compute. It is capital waiting for electricity. And when capital has to wait, value starts to shift. Not away from chips completely. Chips still matter. Models still matter. Cloud platforms still matter. But in the next phase of the AI economy, the key question may change. Not who can announce the biggest AI data center, but who can turn power access into operating compute first. That is the value shift. The visible AI race is still about GPUs, models, demos, and cloud expansion. But the hidden race is about transformers, substations, transmission access, utility approvals, and connection timing. A press release can move in one day. A power transformer cannot. A cloud deal can be signed this quarter. A substation may take years. A company can say it is scaling AI infrastructure. But the grid still has to ask a very simple question. Can this load actually be served? That is the AI bottleneck hiding in plain sight. Chapter 1. Planned compute is not real compute. A modern AI data center is not just a building full of servers. It is a power project with servers inside. That sounds like a small change in wording. It is not. It changes how you should read almost every AI infrastructure announcement. When a company says it is building a massive AI campus, most people focus on the visible numbers. How many billions of dollars? How many chips? How much future capacity? How much square footage? How many jobs? But those are not the first questions value shift asks. The first question is simpler. Is the power already secured? Is the site near available transmission? Are the power transformers ordered? Is the substation upgrade scheduled? Has the utility approved the load? Who pays for the grid upgrade? And when can the site actually turn on? Because before the GPUs can run, electricity has to reach the site. Before electricity reaches the site, the local grid has to handle the load. Before the grid can handle the load, equipment has to arrive. Before the equipment arrives, someone has to manufacture it, buy it, permit it, install it, test it, and connect it. That chain is slow, and when that chain is slow, the bottleneck moves. It moves away from the AI demo. It moves away from the chipstrel.cc/artis/n/slashes/inshady/allspine/artis/beating. Moves toward the physical equipment outside the building. That is why the transformer matters. Not because it is exciting, because it is decisive. A power transformer does not generate images. It does not write code. It does not answer prompts. It does not appear on a keynote stage. But without it, electricity cannot be delivered in the form a data center needs. So the most important object in the AI economy may not always be inside the server rack. Sometimes it is sitting outside the fence. That is the first rule of this phase. Announced compute is not operating compute. Financed compute is not operating compute. Purchased hardware is not operating compute. Compute only becomes real when the site can actually run. This sounds obvious, but it changes where the advantage may move. In the first phase of the AI boom, the question was who could get the best chips. That still matters, but in the next phase, the harder question is who can make those chips productive on schedule. That requires land, permits and/art equipment, utility coordination, power contracts, local approval, and connection timing. You can move fast in a software demo. You cannot always move fast through a grid queue. Chapter 2. The hidden queue behind the AI boom. The AI industry speaks the language of speed. Launch faster, scale faster, train faster, deploy faster. But the power system speaks a different language. Reliability/articolis kolovtiant, percention transgaldavlance in toll. Needy adnobid/articanstating abald. Reliability/articolovtiant. It is the deverance, more and faster operated/articolovtiant. And in the negate phase is the numor du scorrigatin ficor to do honor, have arrived in/bits the nubble tiant/articolovtiant. Legate/minges entering of factories need power. Electric vehicles need charging, homes need cooling. Heat pumps and appliances add load. Then data centers enter the same queue with extremely large concentrated demand. That is the important boundary. This is not an AI-only shortage. AI did not create every grid problem. AI did not magically cause every transformer backlog. AI is not the only force increasing electricity demand, but AI can still change the power structure because it adds a new buyer with unusual urgency, an unusual scale. A normal office building asks for one kind of power. A large AI data center can look much closer to an industrial load. So the question becomes more political, more local, and more strategic. Who gets served first? The data center that promises jobs, the factory expansion, the renewable project waiting for connection, the housing development, the existing customers who do not want higher bills. This is where the conflict starts. The AI industry wants speed to power. Utilities have to protect reliability. Regulators have to protect ratepayers. Communities have to decide whether the benefits are worth the load. And equipment suppliers have to decide who gets the production slat. That is the hidden queue. Not one queue, many queues. The transformer queue, the substation queue, the permitting queue, the local approval queue, the power contract queue, the utility planning queue. And if you want to know which AI infrastructure plans are real, you have to watch the queues, not just the announcements, not just the CapEx number, not just the chip order. The queue tells you whether planned capacity is becoming operating capacity. That is why the IEA's data center electricity forecast matters. Its base case says global data center electricity use could rise from around 415 terawatt-hours in 2024 to around 945 terawatt-hours by 2030. That is not just an energy statistic, it is a warning about AI capacity. If electricity demand grows that fast, the question is no longer only whether companies want more AI compute. The question is whether the physical system can deliver it fast enough. Chapter 3. When the bottleneck turns physical, leverage changes. In the chip phase, the company with access to the best hardware had the obvious advantage. That still matters, but in the power phase, a different set of players can gain leverage. A data center operator with secured grid access becomes more valuable. A site owner near available transmission becomes more valuable. A supplier with transformer production slots becomes more valuable. A utility that controls connection timing becomes more important. A cloud provider that locked long-term power supply early may have an advantage over a competitor that only locked land and servers. And the company spending the most on AI may face an uncomfortable problem. They can have money, they can have chips, they can have customers, they can have demand. But if the power connection is late, some of that capital does not become productive on schedule. This does not mean the AI build-out stops. That would be too simple. It means the payback timeline may depend on details that used to look like background noise: a transformer delivery date, a substation upgrade, a power purchase agreement, a local permitting fight, a queue position, a backup generation plan, a utility tariff. These are not side details anymore. They are part of the AI business model. That is the uncomfortable shift. The winner may not be only the company with the largest model. It may be the company that combines compute ambition with power execution. That is why power equipment is not just an industrial side story. When transformer demand is strong, when cable lead times stretch, when factories report full production, and when orders extend far into the future, the surface story is manufacturing, but the deeper story is control. Physical bottlenecks can move value toward whoever can deliver physical capacity. That does not mean every transformer order is caused by AI. It does not mean every power equipment company automatically wins. It does not mean one country controls the whole AI future. The boundary matters, but when a bottleneck becomes physical, the market starts rewarding different capabilities, not just model quality, delivery, not just software speed execution, not just cloud ambition, power availability. That is why the data center race is no longer only a chip race, it is also a procurement race. Who can lock the transformer? Who can get the substation built? Who can secure the power contract? Who can convince the utility? Who can avoid a multi-year delay? Who can turn a planned campus into operating capacity? That is the race behind the race. Most viewers will keep watching AI product launches. That is fine. Product launches tell you what companies want to do. Power access tells you what they can actually run. Chapter 4. The rulebook is now part of the AI stack. This is the strongest signal that the bottleneck is no longer invisible. It has moved from company presentations into the rulebook. When FERC told grid operators to justify or reform tariffs for data centers and other large energy users, the point was not simply to slow projects down, and it was not simply to let every large load connect as fast as possible. The issue was the trade-off: speed to power on one side, reliability and ratepayer protection on the other. That phrase captures the whole conflict. Large AI loads want faster connection. The grid has to protect reliability. Ordinary customers do not want to pay for upgrades created by a few massive users, so this is no longer only a private construction issue. It is becoming a market design issue. How fast should massive loads connect? Who pays for the upgrades? How do you protect reliability? How do you stop one customer's AI race from becoming everyone else's electricity bill? That is why regulators matter. They may not write the models, but they can shape the timeline. Similar signal is showing up in Texas. ERCOT has been tracking a very large queue of proposed large load requests, with data centers making up most of that queue. Texas regulators approved a framework called Batch Zero to study qualified large projects and manage connection requests. But here is the boundary. A queue is not guaranteed future demand. Some projects will never be built, some will shrink, some will move, some will fail to secure financing, equipment, permits, power, or customers. So do not treat every request as certain electricity demand, but do treat the queue as a signal. Data centers are no longer small background loads, they are becoming grid planning problems. And once something becomes a grid planning problem, the gatekeepers change. The gatekeeper may be a transformer supplier, it may be a utility planner, it may be a regional grid operator, it may be a regulator, it may be a local community. That is the point. The next AI bottleneck may sit outside the data center. Chapter 5. What to watch next. So how do you track this without getting lost in every AI headline? Watch 5 signals. First, watch transformer and cable lead times. If lead times shorten, the bottleneck may ease. If they stretch further, the power gate becomes more valuable. Second, watch large load grid rules. If FERC, regional grid operators, and state regulators create faster but fair connection rules, some projects may move faster. If cost fights grow, delays may continue. Third, watch hyperscaler power deals, long-term power contracts, co-located generation, nuclear agreements, renewable deals, backup systems, and demand response programs will reveal who is serious about turning AI spending into operating capacity. Fourth, watch site selection. Data centers may increasingly follow available power, not just cheap land, tax incentives, or fiber routes. The best site may not be the cheapest site. It may be the site that can turn on. Fifth, watch efficiency. This is the reversal condition. Better chips, better cooling, smarter workload management, and demand response could make each unit of electricity go further. If efficiency improves faster than expected, if transformer supply expands, if grid approvals speed up, and if AI demand growth cools, then the power gate may become less powerful than it looks today. That is the counterargument. This is not a guaranteed crisis. It is a bottleneck test. But if demand keeps rising and physical infrastructure stays slow, the value shift becomes clearer. The AI economy will not only reward the companies that build intelligence, it will reward the companies that can deliver the physical conditions intelligence needs to run. Here is the final judgment. The next AI bottleneck may not be who can announce the biggest data center plan. It may be who can turn power access into usable compute first. That is why gridlocked matters. It is not just a thumbnail phrase, it is a test. When a company announces more AI capacity, ask whether that capacity is already powered. When a developer says data center demand is booming, ask where the transformer slots are. When a cloud provider says it will scale AI infrastructure, ask whether it has secured grid access, power contracts, and realistic timelines. When power equipment suppliers report backlogs, ask whether those backlogs are converting into delivery. And when regulators promise faster connection, ask who pays for the upgrades, because the next AI gatekeeper may not be in the model, not in the demo, not in the chip presentation, but at the point where electricity finally reaches the building. Now I want to know where you stand. If you think the next AI bottleneck is power, comment power. If you think chips are still the real bottleneck, comment chips. And if you think the real risk is that AI demand will not justify all this spending, comment demand. That disagreement is the whole market. If you want to follow the AI economy beyond the headline, subscribe to Value Shift. We track the bottlenecks, gatekeepers, profit pools, and control points behind the biggest business stories, because the headline is temporary. The value shift is not.